All right, let's go ahead and get started. Class 2. Today we will be talking about estimating a population mean, building on the material that we talked about in Class 1. Before I start, I just want to mention if you have any questions on any logistics, any Blackboard problems, any quiz concerns, any questions about how to do the Excel assignments, let me know. You can ask me now, or you can ask me at the break or after class. I know sometimes it's a little overwhelming getting all those working parts moving appropriately, and I don't want to overwhelm anyone with those kind of logistics, at least at first. We'll overwhelm you with the material later in the course as we go, but I just want to make sure you're feeling comfortable on that, and if you have any questions, please ask. So, with that out of the way, we can get to our purpose today of estimating a population mean. So, what is the average income in this town? Alright, that's a number. We want to figure out what it is. Can we ask every single person? Probably not. Can we take a sample? And can we develop some analysis around that sample? That's probably a little more realistic. So we're going to talk about sampling, how we would do that. We'll review the normal distribution, and we'll determine what that tells us about interpreting our sample. And that shows us this really cool thing called the sampling distribution of the sample mean, which will be the focus of our class tonight. That will allow us to develop confidence intervals. All right, we are 95% confident that the income is between 74,000 and 79,000, an interval like that. And then lastly, we'll do some real-world assumptions. Essentially, we'll take some baby steps, we'll assume we know things, and we'll say in the real world we don't know those things, what do we do then? So, with that, estimating a population mean, I mentioned already the example, what is the average income in this town? How much money do teenagers spend on video games? All right, that's an amount. All right, annually they spend this much money, or weekly they spend this much money. If it's a certain amount, we might want to try advertising, we might want to start building new products. If it's less than that, we might want to close our business. So we might need to find that out for an important business reason. Think about how we would. What is the average error rate in my production process? Another example of a population mean. What is the average number of times the coin comes up heads? Remember that experiment we did? We flipped a coin 20 times. What's the average number of times it came up heads? Well, there was a mean that we determined graphically. So we'll go through a thought process assuming we do not know that. And how would we sample for it? All right. So let's talk about sampling. When we sample, let me actually skip ahead to the crux of sampling. When we sample, statisticians use this term statistical inference. I don't want you to get confused by that. That's just a term that means we infer things. Infer. So if we're looking at an entire population, everyone in the town, we'll take a sample, a subset of the town. We will crunch some numbers around that sample, and then we will infer things about the whole population. All right, so that's all statistical inference means. Don't be intimidated by that when you see that in your textbook. We're just inferring based on our sample results what we think the characteristics of the whole population are. So, how do we sample? Well, let me give you an example or a question. Let me pose this question. Suppose we want to find the average income in the town. Do you think we would stand at a bus stop and ask the first 50 people we see, how much money do you make? No. Why would we not do that?
Because you're not going to get a good inference of the overall population.
Good, great job using the terminology. We're not going to be able to infer anything about the whole population. It's just a subset of people who uses the bus. Maybe people who use the bus don't have enough money to afford a car. That's why they're using the bus. We're going to get a biased sample. Similarly, we don't want to stand at the golf club and ask all those people how much money they make. Instead, we want a completely randomized process for our sampling, and we want an equal probability of every single person in town to be in our sample. We want it completely random, and we want an equal probability that every single person will be in our sample. That will give us a good, unbiased sample. Now, that's simple random sampling. Alright, definition, simple random sampling, a method in which ensures every combination of n members of the population has an equal chance of being selected. So, when we do these statistical tests, we'll just say we're assuming a good, simple, random sample. Now, to the question of why we might not want to ask every single person in town, or why that wouldn't be feasible, I think actually I skipped over that part, but let me go back a minute. Well, we may not have the resources to ask every single person in town. We may not even get reliable information if we try to ask every single person in town. We may have to hire a bunch of people to help us with this. They just may be college students trying to make a little money who don't really care about our statistical sample, and so they don't ask the questions the right way. They may try to take shortcuts. It's hard to monitor if we're trying to base results on every single person in this town of, say, 1 million people. And it is actually often better if we can take a good, simple random sample that ensures everyone has an equal probability of being in this sample, and we can have a small number of statisticians asking these questions, or not statisticians asking these questions, workers asking these questions and doing it in an unbiased way, and a way that doesn't influence the results of the sample. So, sample when we can, saves time, saves effort, and can be more precise. When we do it, we want a simple random sampling technique. And lastly, we'll be able to use information from that sample to infer things about the whole population. Alright, so let me do some quick normal distribution review. And where we're going to go with this is we'll think about if we have a sample, how does the normal distribution help us interpret that sample? So, in terms of review, remember we talked about the normal distribution last time. We mentioned the idea, the phenomena, that many things in the natural world will fall into a normal distribution. If I have a forest full of 20,000 trees, I'm going to have an average height of those trees. That would be the mean of my population. And I'm going to have a distribution of those trees. Some of those trees are going to be a little bit taller, some of those trees are going to be a little bit shorter, and the distribution measures how much, on average, each of those trees differ from the average height of the tree. Now, if there's an equal probability that one tree is going to be a little bit taller, a similarly equal probability that one tree is going to be a little bit shorter, if those things are based just on random chance, then it will fall into a nice symmetrical normal distribution like this. And we said, suppose I'm talking on the phone with a guy in China who has another forest full of trees of 20,000, and he measures their heights and puts them on a frequency distribution. And we'd be on the phone, we'd be like, oh my god, that's so weird. My distribution looks exactly the same as yours. He might have a different center, and he might have a different distribution, but the percentage of data would be within the same parameters. And we measure that percentage of data with our standard deviation metric. Alright? We would say one standard deviation contains a certain amount of the data. Does anyone remember what it was?
68.
Yeah, 68.3. I'm jumping around here, let me skip ahead. So, one standard deviation will cover 68.3% of those trees. And so I'm on the phone with this guy in China, I'm like, I measured standard deviation, and 68.3% of my trees are within one standard deviation of the mean. And he says to me, wow, the same thing happened when I measured my trees in China. That's because there was nothing weird going on in his population, there was nothing weird going on in my population, and they fell randomly into a normal distribution. We talked about some things that might skew a normal distribution last time. We looked at different incomes in towns. We said, well, what if there was a group of really, really rich people throwing off the distribution? We might have also had a discussion, which I don't think we had last time, but we could have had a discussion, such as, well, once people start making more money, they have more access to education, they're able to disenfranchise the poor people, and they're able to get even richer. All right? That might be a situation where we would have a really fat tail on the rich end of that distribution, and it would not be random chance who falls on either side of that distribution. But as long as nothing else is going on like that, then we might suspect that things would fall into this normal distribution. And we know things about this normal distribution. The 68.3 within one standard deviation is one of those things we know. We also know 95.5% of the data will fall within 2 standard deviations. All right, how do statisticians know that? Well, they did calculations exactly the same way you all did calculations with the binomial distribution. Remember this? Remember you actually did some of these calculations? All right, if I gave you more time, you could have done all of them. And if I gave you a lot more time, you could have done everything in between all of these. Well, statisticians have done everything in between all of these. And they're able to determine things like, what's the percentage chance that out of 20 coin flips you're going to have 15 or more heads? Well, you would add up the probabilities. You say there's about a 2% chance of that happening. Similarly, there's about a 2% chance of getting 5 or less heads. You might also be able to quantify things as what's the percentage chance that any one student who does this experiment is going to get 9, 10, or 11 heads. What's the percentage chance of that happening? Any one student, I send you home tonight, say flip a coin 20 times, what's the percentage likelihood you're going to get either 9, 10, or 11?
You went up to 3 and take the average, right?
No, just add up to 3. So what is it?
30.
No,
I'm sorry, I just said 9, 10.
9, 10, and 11. What's the probability when you do this experiment, you're going to write down 9 heads, 10 heads, or 11 heads? Well, it looks like about 46. Do you need one of these? Alright, so about 46% chance. The point here is that this is predictable. And these are things statisticians know to be true if they can assume a normal distribution. They know that within this range, there's going to be a 46% chance. 15 or higher, there's going to be a 2% chance. Now I'm using actual numbers here, but when we standardize it, we put it all in a normal distribution, we know things like this. And me and the guy in China are on the phone like, wow, isn't that weird? 68.3% of my trees, 68.3% of your trees were all within one standard deviation of the mean. Alright, this is the great thing if we can assume that things will be in a normal distribution. And if they are subject to just basic laws of probability, random chance, law of large numbers, then things will fall into a normal distribution. Does that all make sense?
Yes.
Right. So, let's do an experiment with this 20 coin flip example. And let's try to sample for the mean of this distribution. So, remember, when we talked about this, we said maybe we could send all 11,000 Mercy College students home and tell them to conduct this experiment. Flip a coin 20 times, write down the number of times it comes up heads. Let's say we do that. We send all 11,000 Mercy College students home and we have them do that. But in this case, we don't have them come back and tell us what they got. It's just too hard to have all 11,000 students come back and report that data to us. Taking a complete census would be too difficult. But we want to know what was the average number of heads that came up for the Mercy College students when they did this experiment. So that's what our goal is. We want to find that number. Now, because we did the calculations already, what is that number? What is the average number of times that this came up heads in this pool of 11,000 students who did this? Was it 20? Was it 21? So 11,000 students went home and flipped a coin 20 times, and they wrote down the number of heads they got. If they had reported all the data back to us, and we crunched the numbers to determine the average number of heads that came up, what would it have been? 10. Yes, we've got one guess for 10. Do we like that? I like that. It would be 10. Yes, it would be 10. Right, that would be the average number of times that we would expect for heads, for students to, for students to come up with heads on this experiment. So if we were to report, if all those 11,000 students were to report back to us, tell us the number of times their experiment came up heads. One student would say it came up 11, another student would say it came up 9, another student might say 12. We add them all up, take the average. The average would be 10. Okay, so the true population mean in this case is 10. Let me write that down. And what's the symbol for population mean?
The mu.
Yes, population mean. All right, so this mu, population mean, equals 10. All right, so that we know to be true because we know the numbers. But let's say we didn't know this in this experiment. We had 11,000 students go home and do this. We heard people talking. We heard people talking in the hallway. One person said, oh, I got 10. Oh, I got 15. Oh, I got 6 heads. Oh, I got 9. We heard things. So we got a sense of maybe what it was, but we want to find out the sample mean. All right, and how do we notate sample mean? With a little X with a bar on it. This is our sample mean. Mean. This equals question mark. Okay, so we want to find, wait a minute. We don't know it yet. All right, we don't know the sample mean. Okay, how am I gonna do this? All right, let me just keep talking and we'll work out those numbers as we go. Where was I? You want to know the population mean. We know it to be 10, but let's just assume we don't know it now. Okay? Is everyone with me there? Just a wink nod. We don't know the population mean. And we're going to determine that by taking a sample mean. All right, we're going to take a simple random sample of a good sized number of students, say 30, and we're going to come up with a sample mean. All right, somebody give me an estimate. What do you think our sample mean is going to come out to?
15.
Just guess. Okay, 15, that's a good guess. All right, that's a perfectly reasonable guess. I was hoping maybe somebody would say something closer to 10, like maybe 10.7 or something like that. So that's going to work better for my example, but you're nothing to say nothing of your estimate. All right, 10.7. 10.7. So yeah, don't ask a question if you know the answer you're looking for. Don't give the students any option of giving a different answer if you know what the exact answer you want. All right. Okay. So we get a sample mean of 10.7. All right. I had a couple of experiments I wanted to go through on the next slide. Suppose we do not know the mean of the 20 coin flips distribution, so you conduct a simple random sample of 30 points of data. All right, what would be the most likely outcome for your sample mean? Now, our sample mean was 10.7. Question for you all, what would be the most likely outcome for your sample mean? Yeah, what's your name again, Ricardo?
Andy.
Andy. All right, why do you say 10, Andy? Yeah, all right. So the most likely outcome for our sample mean would be 10. The reason why it would be 10 is because that is the true population mean. The most likely outcome would be the correct answer. Right? Why wouldn't it be? Why wouldn't the most likely outcome for this experiment be the actual thing we're trying to determine? It would be 10, because that is the most common outcome. Maybe sometimes some of the people we would ask have 9, some of the people we ask have 11, a lot of the people we ask got 10, maybe one of them would have 12, another one might bounce out at 8. Most likely outcome would be 10. All right, next question. How confident are you that your sample mean of 10.7 would be close to the true population mean? Alright, so the true population mean, we know in the back of our heads is 10, but we're just pretending we don't know what it is. Alright, we got 10.7, and I want to ask you, just right now, as statisticians, as statistics students, how confident are you that your sample mean of 10.7 is close to the true population mean of 10? I guess you know, because you know the numbers, it's like 0.7 off. How confident would you be if you didn't know that? How confident would you be that your sample mean is close to the true population mean? Well, I'm looking for two parts to this answer. One, I want to go through some analysis where we would say, yeah, we might be reasonably confident that our sample mean would come out to close to 10. But the second part is we're not able to quantify how confident we are. So, how likely is it, remember we asked this before, how likely is it that any one student would get 9, 10, or 11 for the result of their experiment?
45%.
Like 45%. So of these 30 students we asked, there's a 45% chance that any one of them got 9, 10, or 11. So there's a good chance that most of the students are right in the center already. So there's a good chance that the answer to this question, how confident are your sample mean close to the true population mean, is fairly confident. Another thing that we might have working for us, suppose we were to look at results of 15 or higher. Now remember he said, what are the chances of any one student getting 15 or higher? What did we say that percentage chance was? Around 2%? Alright, so what are the chances of all 30 of our students in the sample getting 15 or higher?
Low.
Extremely low. So it's 30 people, all 2%. It's like 1 in a billion, 1 in a trillion billion, something crazy low like that. So maybe we might have one student get a really high number, which would pull our sample mean off and give us an unrepresentative answer. But the chances of all 30 students being really high and pulling it off, not that high. And there's also an equal probability if we get one student that's really high, we might get one that's really low and balance it out. So that's another point I would make that would make us say, we are fairly confident that our sample mean is in fact close to the true population mean. So, how many students were in this experiment overall? Do you remember?
30,000.
11,000. And how many were in our sample?
30.
30. Okay, so we did a sample of 30 out of 11,000 people, and I think we're comfortable saying that we're fairly confident that we have an accurate estimate. Right? Would you all agree with me? Yeah, I mean, isn't that kind of impressive? Isn't that kind of like a big step? Like just asking 30 people, and that's it. And we're fairly confident that we have a good estimate. You impressed by that? Yeah? Do I want you to be? Fantastic. Alright, yes, question.
Is 30 seems to me like a small number for 11,000 people, but is it because the outcome is 50-50? You know what I mean? It's not like incomes where it could be.
Okay,
A
well,
wide-
income could be a similar distribution, as long as there's nothing weird going on in this town. The income distribution could look exactly like this.
But would you need a larger number or no?
Well, here's the thing, all right, if we ask someone who's really, really rich,
Right.
maybe one person would be really, really rich, but the chances of all 30 of those people being really, really rich and throwing off giving us an inaccurate sample mean, like you said, low, 1 in a billion.
Right.
The chances of us randomly asking 30 people who are all really, really poor and giving us an unrepresentative sample, also really poor. And the chances of most people being in the center of this distribution, also very high, or that is high, because it's normally distributed. Does that make sense?
Yeah, it's just gotta be truly random. Like-
It has to be truly random,
Okay.
yes. And in this case, we're looking at a normal distribution. Okay. So, we are confident and we are impressed that statisticians can say so much with so little, but the thing we cannot do yet is quantify how confident we are. We can't say I'm 80% confident. We can't say I'm 90% confident. We don't know how to do that. In order to do that, we need to take another step. So let's do this experiment a different way, or rather do a different experiment. Let's suppose we were to repeat this exercise of sampling 30 points of data, say 5,000 times. Okay, so we're going to take a simple random sample of 30 students. We're going to write the number, and then we're going to do it again. Take another simple random sample of 30 students. We're going to find the sample mean, note that number, and then we're going to do it again. We're going to do that whole thing 5,000 times. And we're going to graph it. We're going to graph this on a frequency distribution, and we're going to call this frequency distribution sampling distribution of the sample mean. So, sampling distribution of the sample mean. Alright, we're going to have frequency or probability on the vertical axis. We're going to have outcome on the horizontal axis. Frequency. Alright, and so these outcomes, it's going to start at 0, go all the way up to 20. Right in the middle is going to be 10. Alright, so 15 or 5 right, would be here. 15 would be here. Alright, we're going to take a sample mean. The first time we're going to get 10.7, we're going to make a note, 10.7. Alright, we're going to do it again. We're going to get like 10.9. We're going to put a little X at 10.9. We're going to do it again. We're going to get 8.7. Alright, every once in a while we're going to get something crazy like 15. Alright, we're going to make a note. And we're just going to keep adding this up. Alright, each time we get the same number, we're going to put the X on top of each other. We're going to do this 5,000 times. Alright, so same question.
Wait, isn't it 30 points?
So, okay, a sample size of 30. So we're going to take a sample size of 30, and we're going to take the average number of heads that those 30 students got.
Oh, okay.
And we're going to get something like this, 10.7. Out of our 30 students we sampled, we got a sample mean of 10.7. And that's just one time.
They did
We have
4,999 more.
Yeah, we have 4,999 more times to do that exact same thing. Alright, and we're going to keep doing it. Each time we do it, we're going to graph it. We're going to graph it on a frequency distribution. The outcome, the sample mean, how often we got it, frequency on the vertical axis. Alright, so same question I asked you last time. What do you think is going to be the most common outcome on this frequency distribution? 10. Alright, that's going to be the true outcome, the true population mean of 10, and that's going to be the most common outcome. What's your name again?
My name's Lisa.
Lisa, that's right. Okay, and what's your name again?
Charlene.
Charlene?
Charlene.
Sure. Like Shirley or Charlene?
Charlene.
Charlene, Lisa, sure. Okay. Alright, so our most common outcome, Lisa, is going to be what?
10.
10. Alright, why is our most common outcome to be 10?
But you just said that.
What? Was I just saying? Why? Tell me why. Alright, because that's the real answer. Alright, that is the population mean of 10. Alright, so most commonly we're going to get the right answer. Next question. What do you think this distribution is going to look like when we get done doing it 5,000 times?
Normal.
Like a normal.
Normal. It's going to look like a normal distribution. Okay, because the most common outcome is going to be 10. Alright, every once in a while we'll get something a little bit more, or probably frequently, we'll get something a little bit more than 10. Equal probability to getting a little bit less than 10. Alright, unless there's some stigma involved in saying you got fewer coin flips. Hopefully the people who ask questions aren't asking the question in a way that makes the interviewee want to say something like that. So assume it's completely random and good sample. Is equal likelihood a little bit less, equal likelihood a little bit more, as a little bit less. Every once in a while we might get something crazy way out there. Similarly, we might get something crazy way down there the same way. Alright, so the most common outcome of this distribution, the mean of this distribution is going to be 10. It's going to be normal. Now, let's take a look at this question. How confident would you be that any one of your sample means would be within one standard deviation of the true population mean? So let me set that question up a little bit more. You have just done this 5,000 times. You've got a more normally distributed sampling distribution of the sample mean, and you have calculated a standard deviation for this mean. How confident are you that any one of these sample means, like 10.7, would be within one standard deviation of this mean?
Very.
Okay, very. This time you can actually give me a number. And the correct answer is 68.3. So you just took a sample mean of 30, and you are 68.3% confident that you are within one standard deviation of the mean of this, which is the same as the true population mean. How confident would you be that you would be within two standard deviations?
95.5.
95.5. Okay, so now we can answer that question with actual numbers. You took a sample size of 30, and you are 68.3% confident it's within one standard deviation. You're also 95.5% confident it is within two standard deviations. You can actually quantify it because of what you know about the sampling distribution of the sample mean. So let's look at the two characteristics of this sampling distribution of the sample mean. So the mean of this is notated with the mu and a little x bar. Alright, that's the mean of the sampling distribution of the sample mean. That is equal to the true population mean of mu. This also has a standard deviation. So standard deviation of the sampling distribution of the sample mean. Alright, we'll look at that right now. But we'll look at that with this next question. Do you think the standard deviation of this new distribution, i.e. this, is smaller, larger, or the same size as the standard distribution for the whole population?
Same.
So this is the whole population. This is the sampling distribution of the sample mean. So these are our 11,000 students in reality. This is our sampling distribution of the sample mean, where we take sample size of 30 and graph each one. Now, remember we said in the whole population there's a 2% chance of any one student getting 15 or more heads? What are the chances of all 30 students getting 15 or more heads? Very, very low. So in the sampling distribution of the sample mean, this outlier goes to astronomically small. How about for 14? Same thing. Alright, this outlier goes to astronomically small. Because all 30 in our sample would need to randomly be that high, there is a much less probability of it happening on the sampling distribution of the sample mean. So what that means is, this distribution is skinnier and taller, it's tighter, it's smaller. The distribution here is much less than the distribution here. So this bell curve and that bell curve are both normally distributed, but this bell curve is short and fat, this bell curve is tall and skinny. So this bell curve has a smaller standard deviation, and it is calculated this way. It is the standard deviation for the whole population divided by the square root of n, which is the sample size. So suppose we take a sample of 100. What's the square root of 100? 10. Okay, the square root of 100 is 10. So we would divide this standard deviation by 10, and we would get 1/10 the size of the standard deviation on the sampling distribution of the sample mean.
Ooh.
So it's, you with me, Lisa?
Yeah.
Yeah, that was just a lot, so just take in real quick.
Okay, just take a breath. So the answer to this last question on the slide is smaller. So just circle smaller on the slides.
Did you print out the slides this time, or should we print them out before we come? I have them in front of me, that's why I knew that the bell curve was skinnier and taller, but
Okay.
I was cheating. Oh, you did? Oh, fabuloso. Thank you.
No problem.
Thanks, Professor.
Anybody else need slides? Yeah, I'll always have the slides here. Start with them.
Oh, nice, thank you.
Okay. So yeah, just circle smaller there. And then the two key things, the standard deviation of the sampling distribution of the sample mean is equal to the true population mean. This will be on the later slides, but just recap what was important about what we discussed. And the standard deviation of the sampling distribution of the sample mean is the standard deviation for the whole population divided by the square root of n. And there we have it. This is the sampling distribution of the sample mean. And those two concepts, the mean, sampling distribution of the sample mean, equal population mean. Standard deviation, sampling distribution of the sample mean, equals the population mean divided by the square root of n. For sample sizes of 30 or more. Statisticians like at least 30 to assume that the sampling distribution of the sample mean will be normal. If it's less than 30, statisticians are like, well, I can't promise you that this is going to be normal. If it's more than 30, then they say it will be normal. It will be normal, in fact, regardless of the shape of the population, of the parent population. All right, so this concept that Lisa was ahead of me on, the sampling distribution of the sample mean is taller and skinnier than the population distribution for the parent population. Because the chance of this kind of outlier in the parent population, all right, sure, there's a possibility of happening, the possibility of all 30 conforming to that, tiny, absolutely tiny. Okay, all right, how are we feeling on that? Are we feeling good on that? We need to take a breath.
Alright, so
Relax for a minute.
the sample will be less than 30 then always, because the population.
So simple,
is
always
more
has to
than
be
30?
more than 30.
The sample has to be 30 or more,
Okay.
sample size.
For normal.
I feel like you might be confusing in your head sample size and standard deviation. Yeah, so sample size is 30.
Okay.
And then we take a sample size of 30, and we do that 5,000 times, we put it all on a frequency distribution, we get the sampling distribution of the sample mean.
I have a question.
Yeah, one second. Alright, so we put that all on a frequency distribution, we get the sampling distribution of the sample mean. And we know two things about that. We know the mean of that, which is what? What's 10 in this case, but what's the general rule for it?
68.3.
The mean of the sampling distribution of the sample mean is equal to what's mu? Population mean. The mean of the sampling distribution of the sample mean is equal to the population mean. And what else do we know about it? The standard deviation of the sampling distribution of the sample mean is less. It's skinnier than the parent population. And there's a formula specifically for it. The standard deviation of the sampling distribution of the sample mean is equal to parent population mean divided by the square root of n. Does that make sense? What's your name again?
Eliana.
Eliana.
Ileana,
Iliana.
right? Is it?
Eliana.
Oh, Eliana.
Eliana.
Yeah.
Eliana. A question, Charlie?
There's always gonna be like 3 different brackets, right? Like the 68.3, the 95.5, and then there's like a 99.7.
Yeah, I wouldn't say there'll always be 3 different brackets, but those are just 3 things you know. That 68.3% of the data is within one. 95.5 is within 2,
Yeah.
99.7 is within 3 standard deviations. And how do you calculate the standard deviation of this, Charlene?
Not really sure.
Somebody help out Charlene.
My tutor told me that, that's why he made like a little,
Okay, good. Somebody help out Charlene, tell her how we calculate the standard deviation of this?
Of the sample? Or,
The standard deviation of the sampling distribution of the sample mean? How do we calculate that?
that one, right?
Yeah, tell me.
Oh, it's the standard deviation of a sample,
The standard deviation of what? That's,
So the population.
yeah, help us out, Julio. It's the what? This is, what is this symbol
the
mean?
population.
It's up to you.
With the top one, we'll get the square root in it. This is, what's this signal? Of what?
The population,
Divided by what?
square root of
Of what?
Simple sign.
Sample size, yes. Okay, so back to my original question. How do we calculate the standard deviation of the sampling distribution of the sample mean?
the population, deviation divided by square root of n.
Yeah, yeah, yeah. That's how we do it. So we can calculate the standard deviation of the sampling distribution of the sample mean with this formula. Once we have this formula, we know what the likelihood of any one sample mean of 30 is going to be within one standard deviation of the mean. And how likely is that, Charlene?
68.
68.3. Alright. How you feeling, Eliana?
A little bit better.
Okay. Alright. Yeah. So, what should we do here? Should we ruminate on this for a minute? Should we go on to the next slide? Should we ask a question about the sampling distribution of the sample mean? What's your name again? Francisco, help us out. Give us a good question to slow us down here. Otherwise, we have to go on to the next slide. Go ahead.
You want me to give you a question?
Yeah. Ask a question.
Professor, I think to visualize it better, I think if you plug the numbers into, those formula, I think it will at least it will help me out to, make better sense.
Okay. So, what's the true population mean?
10.
10, okay. So what's the mean of the sampling distribution of the sample mean going to be?
10.
10, okay, good. Alright, just suppose the standard deviation of the true population was 5. Okay, and suppose we did a sample size of 30. What would be the standard deviation of the sampling distribution of the sample mean? I'll give you a hint, you probably can't do this in your head. 5 divided by the square root of 30. .91, okay, yeah, so .91. Alright, I like it. So the standard deviation then is gonna be .91. The mean of the sampling distribution, the sample mean, is going to be 10. So, let's see.
So the number here is the total population standard deviation, and we're figuring out the sample size of it? What are we figuring out?
Okay, alright, so we'll just run through this again. So, our goal here was to determine the true population mean. And in order to determine the true population mean, what did we do? We took a sample. What did that sample come out to? 10.7. Okay. And we want to ask the question, how confident are we that that is reasonably close to the true population mean? We know in the back of our head that the true population mean is 10. And it turns out with the sampling distribution of the sample mean, we can quantify exactly how confident we are that any one sample is within a certain number of standard deviations of the true population mean. So if I were to take that sample of 10.7, how confident could I be that that sample is within one standard deviation of the true population mean? Eliana?
What is it, the percentage that we got?
Help us out, Charlie. How confident could I be that that sample is within one standard deviation of the true population mean?
68.5.
Or 68.5?
I mean, sorry, 68.3.
Yeah, 68.3. Alright, so you know what, I think we've kind of got the general idea. We do, right? We've got the general idea.
Yes, it is.
Alright, so, yeah. Are we feeling okay on this sampling distribution and sample mean?
I'm going off track real quick. Is this gonna be the hardest class that we take in our MBA?
Yes.
Cause this is like freaking hard.
Yeah.
You're
I
like
think
a
so.
doctor in this, but like we're like in first grade in this. So like this is college for you, first grade.
Yeah, yes, I think this is the hardest class you will take
Yeah.
in your MBA career.
Oh,
Oh,
God, I hope
baby
so.
Jesus.
I hope so. Alright,
I'm speaking of foreign language tonight.
let
Sample
me,
distribution of the sample mean, come on. You don't talk this
You
language
know.
every day?
how should we do this? Let's just go back. Let's do this slide and this slide again. Okay, you wanna do these two slides again? Alright, let's do the two slides from the beginning. Alright. So suppose we did not know the mean of the 20 coin flip distribution. So we conducted a random sample, 30 points of data. We got, say, a sample mean of 9.4. Alright? How confident are you, no wait a minute. What would be the most likely outcome for this sample mean? We got 9.4, but what's the most likely outcome? What would it have been before we got 9.4?
10.
Yeah, it would be 10. Why wouldn't it be 10? Because that's the actual answer. The true population mean is 10, so the most likely outcome would be the real answer. Second question, how confident are you that this sample mean, 9.4, is close to the true population mean? Fairly confident? Yeah, I think we decided that we're fairly confident. The reason we said we're fairly confident is because, look at this distribution. How likely is it that we would get 9, 10, or 11?
Likely.
40%. So any one of those 30 students, there's a 45% chance they're gonna say 9, 10, or 11. So most of our students who respond to this survey are gonna be right in the center, and they're gonna give us an accurate representation of the true population mean, right? How likely is it that any one student gives us 15 or more? Well, 2%, right? Okay, so it could happen. It might happen in our sample, but are all 30 of our students gonna say 15 or more?
No.
Tiny percent chance of that happening. So in answer to this question, how confident are you that your sample mean would be close to the true population mean? I think we went through a discussion where we said we would be fairly confident for those two reasons. That out of a population of 11,000 students, we sampled just 30, and out of that, we're pretty confident, we're feeling pretty good that we've got a reasonable answer. This 9.4, that's a reasonable answer. Okay, so we like that? Alright, we can say reasonable answer, but we can't say how confident we are. We can't say I'm 68.3, we can't say I'm 100%, we can't say I'm 90%. We can't quantify it whatsoever. And what we want to do is find a way where we can quantify it. How can we give a number of how confident we are? So let's do this experiment again, or do a slightly different experiment. Let's suppose we were to repeat sampling these 30 points of data 5,000 times. After each sample, we plot the sample mean on a frequency distribution, and we call this distribution the sampling distribution of the sample mean. So, sampling distribution of the sample mean. Alright, so what goes on the vertical axis?
Frequency.
Frequency, I like it. Frequency. What goes on the horizontal axis?
Outcome.
Outcome. Alright, out. Alright, what's the lowest number on our outcome? What's this number here?
0.
0. Because it is possible that the outcome could be 0 heads. Extremely small, but it's possible. There's also a possibility the sample could come out to 20. That's possible, very small. The middle is going to be 10. Alright, so we're going to take a sample mean, like we did here, and we get 9.4, and then we're going to write 9.4. We're going to put a little x by 9.4. What are we going to do next, Ileana?
Fill it in.
Well, we did it once. How many times are we going to do it? Okay, so walk me through. What am I going to do now? I've just one sample mean. What do I do next? I take a sample of size 30, right? And then what do?
Get the next.
I calculate the sample mean, and it comes out to, say, 10.1, right? And then I write a little check mark by 10.1. Alright, I'm sorry, it was one of those like simple questions that was confusing, because you were lost in my thought process. Now what do? I do it again.
Yeah.
I get a sample mean, I put a little x, I do this 5,000 times. Okay? I put a little x every time. What is the most likely outcome for what am I going to get most of the time? What's the most likely sample mean I'm going to get? 10. Okay, so 10 is going to be the highest point of this distribution. Alright, what is this distribution going to look like?
Normal.
Normal. Why is it going to look normal?
It's going to follow the population.
It's not that it's going to follow the population, because we'll find that it doesn't matter what the population looks like. It's going to be normal because it's completely random. Because the most common outcome is going to be here, and then there's an equal probability of getting a sample mean a little bit higher than 10 as a little bit lower than 10. There's an equal probability of getting a sample mean of 12 as a sample mean of 8. Those things are both the exact same likelihood. So this is going to look normal. It is going to be normal. So this is our sampling distribution of the sample mean. It's going to have a mean, sampling distribution of the sample mean is going to be equal to the true population mean. So the mean of this normal distribution is going to be equal to the true population mean. And it's going to be normal. Next question. How confident would you be that any one of your sample means would be within one standard deviation of the true population mean? So one of our sample means, let's just say it's 10.3. How confident would you be that that is within one standard deviation of the true population mean?
68.3%.
You'd be 68.3% confident. Because you know that in any normal distribution, 68.3% of the data, 68.3% of the data falls within one standard deviation of the mean. And we know that the mean of this is the true population mean. So we have a sample mean of 9.4, and I am able to say that I am 68.3% confident that that is within 1 standard deviation of the true population mean. And our goal here is to determine what the true population mean is. We want a number. We want to go to our boss and say, here's the true population mean. But instead we're going to go to our boss and we're going to say, this is a sample mean of 9.4. I'm 68.3% confident it's within 1 standard deviation. Maybe our boss wants a higher level of confidence. So what do we say in that case, Charlene?
Negotiate. 95%. Within 2.
Go ahead, Francisco?
Yeah.
Yeah,
You'll be 99.5 confident within
95.5, yeah. You say, okay, you want a higher level of confidence? Fine, I'm 95.5% confident that it's within 2 standard deviations of the mean. You want to be even more confident than that? What do you say, Susie?
I'm, 99, whatever it is.
99.7.
7% confident that it's within 3 standard deviations of the mean.
Yeah. Yes. Okay. So that's our sampling distribution of the sample mean. And then the last thing I asked is, do you think the standard deviation of this sampling distribution of the sample mean is smaller, larger, or the same as the population?
Small.
So this is the population, this is the sampling distribution of the sample mean.
Small.
And it's much smaller because the chances of getting heads 15 times for any one student, 2%. The chances of all 30 students getting heads 15 times, tiny. So this sampling distribution and sample mean is going to be skinnier and taller. It's going to have a tighter confidence interval. So when you go to your boss and you say 1 standard deviation, it's going to be a smaller number. You're going to be able to give your boss more precise information. All we need to do is add 3, subtract 3, or add 2.7, subtract 2.7, whatever it is. Okay. Eliana.
Much clearer.
All right.
Thank you.
You bet, you bet, you bet. All right. So sampling distribution of the sample mean is the probability distribution, which we did, of all the values of the sample mean when sample size of n is taken from a given population. To produce this, we would at least conceptually generate all possible sizes. We would do this infinite number of times. We would put this in a frequency distribution. And for large enough sample sizes, size of 30 or more, this is normal. That's the key. This is normal. We can assume it's normal. It has certain qualities that we went over and that were on the slide before. The mean of the sampling distribution of the sample mean is equal to the true population mean. The standard deviation of the sampling distribution of the sample mean is smaller than the population standard deviation. And it's smaller calculated by dividing it by the square root of the sample size. Statisticians call this the central limit theorem. Don't get confused by this. This is just restated what we've just gone over with the sampling distribution. Yes, Susie?
Why don't they come up with 30? Like 30 being the number that under 30 they can't be that confident, but over 30 they're much more confident that's gonna.
Honestly, I don't know. They just did through trial and error. They said, when we do sample sizes of 29, they must have had some calculus equation which said 29, it may not be normal, or it's getting normal. Sample size of 25. Yeah, they went through something very complicated and proved it somehow. And we just went through an intuitive, well, if you ask 30 people, what are the chances of all 30 of them getting a really extreme example? Really, really tiny.
Right.
So that was good enough for us now, but statisticians went through a much more rigorous proof and decided 30 was the right number. Good question. All right, so central limit theorem. So it's this thing. As the sample size increases from 2 to 5 to 10 to 30, then the distribution of this sampling distribution of the sample mean approaches the bell curve of normal distribution, regardless of the shape of the parent population. So our parent population with the coin flip, that was normally distributed.